Hi there, and welcome to this session on electrodynamics. My name is Heinrich Cox, and I'm looking forward to spending this time with you to unpack some of the things that you need to know for electrodynamics exam success. Let's get going. Now, the first thing that we need to talk about are generators. Now, generators are those things that have the particular energy conversion where we take mechanical energy, right? And we take the mechanical energy and we turn it into electrical energy. And that electrical energy we end up using in our houses or that sort of thing, because that is actually how Eskom gets us our power, right? So our mechanical energy is turned into electrical energy by a generator. Now the question is, how on earth does it do this? And it does it through this principle that you might have heard about, which is electromagnetic induction. Okay, so electromagnetic induction, right? And then the question is, well, what needs to be present in order for electromagnetic induction to take place? And the answer to that is there has to be a change in magnetic flux. Okay, so there has to be a change in magnetic flux. There's supposed to be a triangle that says delta. Okay, so there's got to be a change in magnetic flux. And then the question is, well, how on earth do we get a change in magnetic flux from this particular machine, right? So what we'll do is we'll rotate this armature, or you can also call it the coil, in the magnetic field. And you might have seen a formula that looks something like this. Flux is equal to AB cos theta, where that theta gave us a particular relationship between the coil and the magnetic field lines. Now, since you're not going to do a calculation on this, you don't have to actually remember exactly what the calculation is or what the relationship is, but this theta here, the angle between that normal to the plane of the coil and the field lines, that thing there is going to be changing, right, when we rotate something. So by changing this theta here, we're going to be changing the flux. And whenever you have a change in magnetic flux, that is what you need in order to have the induced EMF. So that change in magnetic flux by rotating the armature in the magnetic field, that is what causes the electromagnetic induction, in other words, the current to flow. Now, if we look at this here, we can identify some of the components, right? So I'm sure you can identify by now that these two things here are going to be magnets. Okay, then I've used this terminology now in my explanation, but let's write it down. This is the armature, or we can call it the coil. Now, these two things here, those we call slip rings. Okay, so those are slip rings, and then these things here, those are carbon brushes. Okay, right, so those are our components. So let's talk about what some of these components do. Now, the magnets are obvious. They create the magnetic field. The armature is that thing which rotates in the magnetic field. And it's within the armature, the conductors that go around in order to make that loop, that we actually get the magnetic flux. So in the armature is where the magic happens and we actually get current flowing. Now, through the slip rings, the armature is connected to the brushes. So those carbon brushes are able to conduct electricity. They'll be made of graphite, which is a particular allotrope of carbon that conducts electricity. So they'll be made of graphite, and what's happening is those slip rings, as the armature rotates, is going to be sliding against the brushes so that they're constantly in contact with those brushes. And through that contact, the current that is being generated within that armature is going to move to the slip rings and then through the brushes to the external circuit. So in combination with the slip rings and the brushes, the armature is connected to the external circuit, and that's how the current gets from the armature where it's being generated to the external circuit where it can actually be used in some sort of useful way. Now, they might ask you, or you might be wondering, why on earth are these brushes made out of carbon and not maybe something like copper, which is a metal, right? So graphite has a very, very low coefficient of friction. In other words, things can move against graphite very easily, which means that there's lower friction between these slip rings that are actually moving against these brushes. And if there's less friction, it means less of our energy is going to be wasted just trying to rotate the thing against friction, and more of it is going to be turned into electrical energy. The other reason is that to replace the slip rings themselves is a little bit more expensive than it would be to just replace the carbon brushes. So by using the carbon brushes that are made of the softer graphite, the brushes wear away over time rather than the slip rings. And so the slip rings are not going to wear away at the same rate, and when the time comes, you can simply replace the carbon brushes cheaply rather than having to replace the slip rings or basically the whole armature, since the armature will be attached to that. Okay, so that's why those brushes are made of carbon, right? And now that we understand what the role is of each of these things, we can now make a statement, right? And that statement that I'd like to make is that when we have these slip rings, the slip rings are the component that allows us to have an AC generator. Okay. AC generator, so AC stands for alternating current. So when we're talking about alternating current, we're talking about current that flows in one direction, then the other direction, then the other direction, etc., etc. So it alternates, going back and forth. Right, so why does the slip rings give us alternating current? Well, whenever this armature rotates past the vertical, right? So the vertical is when it's in this position here, where you would kind of describe it as being upright. Okay. So whenever this armature rotates past the vertical, the current in the armature reverses. Okay. So every 180 degrees, it's going to go past that vertical point, and at that point, the current in the armature is going to reverse. Now, due to the slip rings, the same side of the armature, and here I've got it in pink and in green, the same side of the armature is always connected to the same side of the circuit, right? So the green is always going to be connected to this brush, and the pink is always going to be connected to that brush. So what does that mean? It means that every time the current alternates, starts going the other way within the armature, that same thing is going to happen in the external circuit. And so in the external circuit, we also get AC current. So what might this look like? So AC current has this sinusoidal form like this. So it looks like a sine graph. But whether it's going to be a sine graph or a cos graph depends on where we start in the rotation, right? So when we have this 0 here, so I should probably say that this is EMF versus time, but it could also be current versus time, because current and EMF are going to be in phase due to Ohm's law, right? So we're going to think here, right, what position is going to give us this 0 for EMF, right, where there's going to be no induced EMF? What's going to give us a maximum induced EMF, which is going to be these bits here? And let's see. Okay, so when we've got the armature in this vertical position like this, right? So within the magnetic field, it's going to look something like that, right? that is when we're going to have zero induced EMF. So it's in this vertical position that we don't have a current. Then 90 degrees later, that is when we're going to have a maximum induced EMF. So the maximum induced EMF is going to take place when the plane of this armature is horizontal. Okay, so when it's in that position there, and so far we've only rotated 90 degrees. Now, if you rotate another 90 degrees, you're again going to get to a position where you are vertical. Another 90 degrees, the armature is going to be horizontal. And then here, when we finally rotate another 90 degrees, you'll see that actually in total you've rotated 360 degrees. So that then means you get back to where you started, which is what we had at this point here. Okay, so that's how the position of the armature in the magnetic field relates to that output graph that we get for the AC that comes out, right? So when I say out, I mean in this wires here that goes somewhere to an external circuit where, well, the electricity gets used in a useful way to turn on a light bulb or to run a fan or whatever it is. Okay, cool. So then we might think of the examples of where we actually use AC generators. And AC generators are by far the most common form of a generator because that's what ESCOM uses in order to give us electricity when they do manage to do it, right? So they take coal and they use that coal in order to create heat. And then from that heat, they warm up water until it turns into steam. And then that steam is used to turn a turbine, and then within that turbine is that AC generator, which then gives us the alternating current. Okay, so let's now talk about the DC generator. And you'll see that the diagram is not particularly different. The only thing that has changed is instead of having the slip rings here, we are going to have a split ring, also known as a commutator. Okay, so you've got a split ring, also known as a commutator, when we have a DC generator. Okay, now in terms of the principles, the energy conversion is still going to be the same. We still have mechanical energy that's being turned into electrical energy. It still operates on the principle of magnetic induction and electromagnetic induction, and this is still occurring because of the change in flux, because of the fact that we're rotating the armature. Okay, so that's all the same as it was for AC, but now the only question is, well, what changes with the split ring commutator? Now, you might recall that I said for the armature rotating in the magnetic field, every time it goes past the vertical, the current in that armature is going to reverse. It's going to go the other way, all right? Now here, the split ring is kind of tricky, right? Because here, if you see this side, which is connected to the green, if that armature goes all the way around, that green side is actually going to be attached to the other side of the circuit, right? And then same thing for the pink. The pink that is now connected on the south side, that is actually now going to be connected on the north side, right? So what does this mean? It means that as soon as the current changes direction within the armature, the side that the armature, or a particular side of the armature, is connected to changes because of the split ring. So as the current reverses in the armature, the sides that the armatures are connected to also reverses, and if you reverse a reverse, well, you get what you started at. So that means that in the external circuit, the current is going to continue flowing in the same direction, right? So a DC generator is going to give us an output that looks like this for a 360-degree rotation, whether we're talking about the EMF or the current. And basically, it's like taking a AC generator and generating what we would call an absolute value function of that. So what on earth does that mean? It just means that as soon as the graph wants to go below the x-axis, we say, nah, you can take the same path, but you've got to go above the x-axis. Right, so that's a DC generator. And the important thing is that you note the component that is necessary for the DC generator. It is a split ring or a commutator, as you see in the diagram there. Now, what do we use a DC generator for? Well, one example would be the current that we require in order to charge batteries. So you might recall from your electrochemistry that galvanic cells and electrochemical cells, they tend to work with DC current. Now, in order to charge a battery, we need DC current, and so a DC generator might be useful in order to charge a battery. All right. So then we want to be able to determine the direction in which the current is going to flow in the armature, right? If we do know the direction of the rotation. Okay, so let's say, for example, this armature here is rotating clockwise. So the green's going up and the pink there is going down. Okay, now in order to find the direction of the current flow, we are going to use the right-hand generator rule. Okay, and the way I remember it is I always think, well, if I'm going to have to crank a generator, you know, something that I've got to input the mechanical energy to get the electrical energy, well, I would use my right hand because I'm right-handed. Okay, so that won't work for lefties. Sorry about that, but that's how I remember it. What would I crank a generator with? Well, my right hand. Okay, so right-hand generator rule. And what we're going to do is we're going to start off with finger guns, right? I'm not trying to be cool, although math, well, this isn't math. It's a little bit maths, but science is cool, so, you know, finger guns for that. But we start with the finger guns, and then we decide, okay, our middle finger has to come out perpendicularly from our palm, right? So that means we actually have these three fingers that are orthogonal to each other, which is a fancy way of saying perpendicular in the 3D sense, and they're all pointing in different directions, right? Okay, so once we've got our hand in the appropriate way, we've got to know what each of these fingers are going to represent. Now, a common way of remembering this is to use FBI, where the F is going to be for the force, the B is that thing that we often use for the field, right? So I showed you earlier that the flux is equal to AB cos theta, right? In that particular equation there, the B represents the magnetic field. And then the I, no surprises, I hope, is going to be the current. Okay, so we've got FBI, right? And again, we don't want to hold it like this, we want to hold it like this. Now, we've got to start with the force, I guess. And what you'll notice is that the green side actually has a force going upwards, and the pink side actually has a force going downwards. So you've got to be careful. You can't use both sides at the same time because the force is going in opposite directions. So you've got to choose a side of your armature, right? So I'm going to choose the green side, which means you get the thumbs up. The force is going to go upwards, right? Then the next thing is, well, in which direction does the magnetic field go? Well, the magnetic field always goes north to south, right? So with your index finger, you've got to be pointing from north to south. And then if your middle finger is facing away from your palm like it should be, well, then it's facing away from you, right? Which means that in this instance here, the current is going to be flowing in that direction. So if we call this A and that B, then the current is flowing A to B. And just something to note here, when we talk about current in electric circuits and electrodynamics in the physics section, we talk about conventional current. And conventional current is, well, basically the convention that the current flows from positive to negative. And that is actually the opposite to the flow of electrons. Electrons in the circuit actually flow from negative to positive. But we're dealing with conventional current here. Okay, now if you had picked the pink conductor, you would still get the same answer, right? Because you'd now have your force going downwards, but then to point north to south, you might contort in this sort of position here, and then your middle finger would be going towards you, right? So this would be in that direction, which is consistent because in order for the current to go around like it's supposed to, well, it's got to go away from us on the green side and then towards us on the pink side. So everything worked out exactly as we hoped that it would. Okay. So, something that I remember from my days writing exams, not that long ago, is the fun of seeing when your friends are busy with the electrodynamics section, because all of a sudden people are busy contorting themselves in all sorts of ways to figure that out. So look out for that during your exam, you might be entertained. Okay. So then, when we talk about generators, we know that we're using mechanical energy in order to output electrical energy. But maybe we'd like to change how much electrical energy we're actually getting out. Right, so we need to know what we can change about our generator in order to increase the EMF. Okay, now you might recall an equation that looks like this. The EMF is equal to negative N times the rate of change of flux. Okay, and this is an equation that shows us, for example, Lenz's law, where the negative gets multiplied by that rate of change of flux to give us the EMF. And it also actually shows us Faraday's law because it shows that the EMF is directly proportional to the rate of change of flux. Okay, now we don't need to do calculations here, but this equation is actually kind of useful to help us remember the ways in which we can increase the EMF. Now, the one way that we can do it is to increase that N, and that N is the number of turns in the coil. So how do we do that? Well, let's imagine our coil is coming around this way, right? But instead of now going back to the circuit or back to the slip ring it's connected to, it actually just goes around once more, right? So now we would have 2 turns in the coil, or we could go around once more, and now we would have 3 turns in the coil, and then so on and so forth until we have many, many turns, and then only do we go back. Right? So that's the one way that we can increase the EMF, is we can increase the number of turns in the coil, or the armature, if you prefer. Okay, so then the other thing there is the rate of change of flux, right? Now, a rate of change is how quickly something happens. So if you do it faster, well, then the rate of change is going to increase, right? So what does that mean? Well, it means that if we rotate faster, we are going to increase the EMF because we'll be increasing the rate of change. So then the other thing is to see how we can increase that change in flux term. Now again, the flux is equal to AB cos theta, as we said, right? Now here, the A isn't really a term that's easily manipulated because it's actually this surface area that's enclosed by the loop of wire, right? So that's not easy to change, so we don't usually think about that. But the B, the magnetic field strength, that we can change, right? So you can increase the EMF by using stronger magnets. Okay? And then this theta term, we can kind of fiddle with that as well by using curved magnets. So curved magnets just basically mean that the armature is going to be cutting the field lines at an ideal angle more of the time, and so we'll get a greater induced EMF. So those are 4 ways that we can increase the output of our generator, which is, kind of useful, because, the more we can get out, the better.